Well, thank you for listening today. I'm going to be sharing with you about the advanced mathematics. I'd like to thank my team of markers who all worked very hard to ensure consistency of marking with very trying circumstances last year with things remotely. I'll be looking at questions 11, 15, 20 and 22, and some of these questions were common questions with the standard markers, and so we worked together to ensure consistency of marking across both courses. So my first question is question 11, and this was a common question with the standard markers. It was a very well attempted question, and most students had no trouble at all. However, there were some common errors, and that would be incorrectly plotting the x-intercept or starting the graph at the origin, heading upwards, drawing a curve rather than a straight line. And a few students really only looked at the grid itself and constructed their own graph on that grid, ignoring the scale already provided. So I think the key takeaways from this one is the constructions could be problematic. So I know for advanced, we're often getting the students to sketch. It's really good to try some of these problems where they're going to be graphing accurately and they've been given an accurate grid on which to do that. Next, I think, is that students need to have a ruler. What many students did was simply use whatever they had to hand. So if that was a calculator edge, then you would see a kink in the line, or some of them used the booklet edge and you would see the stapler marks along their line. So what I would recommend really is that students are now bringing a 30cm ruler to the exam. Those students who had small rulers or parts of rulers, you would often see a small kink in their line and might get a straight line for a bit, and then when they transferred to the second part with their ruler, you'd get that change of gradient. So a 30cm ruler, I think, would be really good. All right. I'm not sure how to get, do I have to go back and rub that off? All right, in part B, this was also very well attempted. Many of our advanced students did solve using simultaneous equations algebraically, and most could read the point of intersection if they'd used the graphs. Some of the errors that we saw were incorrect or poorly constructed graphs. One common mistake that I saw was that the students would start their graph for tank B at the point 15, 20. I couldn't see a reason for that, but that was quite common to start just up above the axis. Some also determined that the equation for tank B was VB equals 30T. So just an incorrect or a simplified version there. So I'd say the learning outcome from this one is that the quickest method for this particular question was really to make a neat ruled line and inspect it. So to be good, it was good to see that students were able to recognise and utilise simultaneous equations, but this would be taking time from the other questions. The standard students were prepared and ready to use the graphical methods. And given that the scale was provided and the graph was large enough for accurate graphing, the graphical method was certainly the most efficient. In part C, again, quite well done. It was easily solved if you'd already constructed a nice graph, and certainly those who used the simultaneous equations method also had two values that they could get the sum from. It was common, however, for students to simply find where tank B reached 1,000 instead of looking for the sum. So we saw that as a solution quite a lot. And the other problem was simply taking t equals 0, which is excluded as one of the solutions in the question. So again, as a learning outcome, the graphical method was going to be the most efficient, and we need to demonstrate to students when this method might be more appropriate so they can save their time for more complex problems. So question 15. Again, quite well attempted. This is another common question with standard. Most, I was quite surprised, interpreted the information in the question and were able to come up with the correct sum. There were a few students who were trying to fudge, they didn't have the geometry, and they would work backwards from part B, having found the length already. So in part B, you needed to find the length, and that was, again, generally very well attempted. There was some errors with the using of the 100 from the previous information rather than the correct angle that they had of 65. There was some misuse of the sine rule instead of the cosine rule, and a small number of students who wrote an incorrect cosine rule. So generally that was missing the multiplier of 2 or the minus sign, just some mix up with that particular rule. In part C, again, we had strong attempts to find an angle within the triangle, and using the sine rule to find an angle proved to be an efficient method. Where students perhaps not getting full marks, there was an attempt to use geometry only to find various angles within the triangle, and you can see even on the diagram you've got your compass markings, so they were then translated as well at B, and so there was an attempt to use parallel lines to try and work out angles. Some also attempted to use right-angled triangles, creating right-angled triangles within the shape to try and find angles and then supplement this with geometry. Many were able to use the sine rule or the cosine rule to find one of the angles within the triangle, but then they neglected to move on to find a bearing. That was most often done when they'd found the angle at B. So learning outcome, there was a lot of working clearly presented in all three parts of this question, and it was really good to see that well set out working, maybe a result of the fact that they're working now within the booklet, so it was quite clear what they were working on and that their working was directed towards those parts of the question. I can see why many people stopped once they'd found an angle within the question. They thought that that was worth, within the triangle. They thought that was worth 2 marks, but I think it's really important to encourage the students to reread that question and make sure that they have found what was actually being asked for, not an angle in the triangle, but the bearing. This question was not a common question. So it was well done again. Most students worked pretty quickly to state the correct expression, and I did see some other methods attempted. One was clear working out of individual trapeziums and then summing them, but again that method's inefficient, taking up their time. Probably the most common error was the use of the 6 instead of the 5 strips, and there was also some use of t values instead of function values in the formula. So I suppose the clear takeout from that is we still need work to support students understanding the trapezoidal rule, with particular focus on how many strips they're using, or finding the height correctly, depending on which formula they're going to use. Question 22, again a common question, and we haven't seen very many questions like this before, but I found it to be a really good question, offering the students scope to actually solve problems. It wasn't stepped out for them, and there were multiple pathways they could choose to find the solution. So certainly you can see the three common ways there to start the problem. One is to use your right trig by putting a height in, or to go with the cosine rule with two unknowns, or to go with the sine rule, knowing the two angles. Students did find this challenging, so it'd be really good, I think, to include questions like this that are worth significant marks in your own assessments, and leave the students the space to work their way through a multi-stage problem. So it's kind of structured how I'll talk about this differently. I'm just going to focus here on, that initial step. So the first thing you would do is find the measurements. And so most could find the length of the decagon, but some did choose 10 for the length AB. Most were able to find the angles of the triangle, but there were incorrect values given, and common ones included 81, 144, 60, 30, 45. They seem to be just choosing things they thought would be common for triangles. If trigonometry wasn't attempted to find one of the other sides of the triangle, it was often assumed that OB was 8 and that this was an equilateral triangle. And if trigonometry was attempted to find a side or a height, we saw a wide range of success with this. So many different methods were attempted. So we saw the sine, the cosine rule, right angled trigonometry, and often this was combined with Pythagoras theorem. So either to find the height of their triangle AOB, or having found the height of their triangle AOB, looking for the side OB. The next stage then would be to find the area of one of those triangles. And so attempting to find the area of triangle is something that most could do from the values they'd previously found. However, some used the wrong area rule for the information they had collected, or used the wrong combination of sides for their rule. So an example of that might be that they had 8 and they had their 12.9 and they had their 72 and 36, but they used the base times height rule with 8 and 12.9, or they might have used the half AB sine C, but used 36 for their sine instead of the 72. Some did try to find other kinds of areas. The sector was the most common. They had the angle, and so they went for pi r squared times the angle they've got. But we also saw them calculate that area as a trapezium or a rectangle. They were a little lower kind of students. When they were using the half AB sine theta, students who recognised that A equaled B often tried to shortcut their substitution, and they were confusing squaring with multiplying by 2. So let's say they'd assumed the 8 times 8, that it was an equilateral triangle. We've got this formula here, half times 8 squared times sine theta, but they'd interpreted the 8 squared to be 16. So we did see that a fair bit. So it was a real problem that the difference between square and timesing by 2. And some students found the height, but when they did that, they didn't find the correct triangle. So, for example, they've come in and they've looked for this here, but then when they have found that, they're going to need to either double it and times by 10 or times by 20 to get the whole amount. Many of them just found that area and times by 10. And then moving on to complete the problem. Most students had no trouble timesing whatever area they'd come up with by 10, but we did see some students multiplying by 8 or 9, and some did forget to multiply after finding the area of their triangle. We did see an occasional alternate method. Finding the area of a circle and subtracting 10 segments was a really nice and efficient method, so long as the students were really confident with their rules in algebra. All right. I just noticed the error in my presentation, and in that first point there, it should have said triangle. So some forgot to multiply by 10 after finding the area of their triangle.